Hi everybody, today I'm going to talk to you about types of forces, and so I've drawn some out for you so we can talk real quickly about them. This should be a pretty easy concept for you. Uh, we just want to introduce some of the forces that you're going to see in the class over the course of the year, and we'll talk about each and every one of these at some point, so we want to make sure that you have a little bit of background on them. Some of them more than others though, so I'll try to point out which ones are going to be de-emphasized as we go along. I want to just talk about, before we get too far into it, the fact that we have really two different types. And so the first type right here, we would call contact forces. Contact forces, just like the name implies, are forces that are transferred through touching, right? So through two objects that actually touch, we'll apply a force to each other. And so there are many types of those contact forces, and we're going to talk about those in just a minute. The second type is field forces, and field forces do not touch. So there's nothing that touches physically that causes the force to be transmitted from one place to another. It's really through this idea called a field that we'll talk about in just a minute. Okay, so we're going to start with contact forces. They're the easiest ones. If I told you to imagine applying a force to something, you would probably imagine a contact force. So let's imagine that we have, we're going to talk about those, and let's imagine that we have this box and it's sitting on a floor. Okay, so we're going to use this guy right here as a possible example. So that guy looks kind of grumpy. He looks like somebody left this stupid box in the middle of the floor. I need to get out of the way. So he's trying to push it out of the way, but he looks like he's having a hard time with it. Okay, what kind of forces are being applied here? Through touch, through contact, okay? And so let's take a look at it here. Well, obviously the guy is pushing in this direction right there. And so I'm going to go ahead and draw that, like so. He's got an applied force. And I think you'd agree that he is applying the force through actual physical contact with the box. Okay? Now, if you've ever tried to do this yourself, you know that anytime you try to slide something across the floor, there is another force in there that resists that sliding, and that is friction. Now, for the obvious reason that F sub F would look weird, for friction, we usually do it a lowercase f, like so. So there, that's, if you see that lowercase f, that's what that means. Next, there's a third contact force in there that you maybe didn't think about, and that is in response to the question, is the box falling? You say, no, of course not. So there must be stopping it from falling. There must be something stopping it from falling. And I think you'd agree it's the surface, the floor right there, right? And so there must be an upward force as well. And rather than call it the supporting force, it has a special name, and that name is right there, the normal force. Now, just as a spoiler alert here, normal means perpendicular. So the normal force is the force that the surface that's supporting an object provides, and it's always perpendicular to that surface. So the word normal means perpendicular. Just keep that in mind because I'm going to use the word perpendicular, or excuse me, the word normal all the time, and I'm going to assume you know it means perpendicular. I'm running out of room. There we go. Okay, good enough. You get the idea. Okay, so normal means perpendicular. So those are the three contact forces that are happening when you try to slide a box across the room. There is a fourth force, but it's not a contact force, and so we'll talk about what that looks like in just a second here. I also drew a little Jeep down here, sort of, as best I could in this scenario here, so that we could look at two other forces. So one of the forces that you can think about here, if you're riding this Jeep and it's going over a bumpy terrain, I want you to think about what's happening inside the wheel wells here, and that is they have these spring shocks like that. And so if you looked at them really close, you'd see these cylinders have a central post like so, and then they have this coil of springs that go through there. And as the wheel gets pushed up, the coil gets shoved together like so. And so we have compression. And so you can have a compression force. And then when it gets spread apart, so you get the coils all stretched out like that, you've got a tension force, which you could do F sub 10 if you wanted to, or some people do a capital T right there. I don't like capital T because it also means the period of an object, or the temperature of an object. So for me, capital T is restricted, but so I usually do F sub 10. So if you see that, you'll know what I'm talking about. And again, that's for tension. Tension works for springs, it works for ropes, it works for anything that applies a force over a wide distance. So it actually transmits a force through that medium. So those are really the main types of contact forces there. Now there's one other that's kind of a weird way to think about it. So let's say this Jeep has some velocity going forward. So what is it moving through? Well, it's moving through the air, right? And so the air must also be applying a contact force backwards. And so we have the drag force right there. It's an air resistance force, and it acts in the opposite direction of motion. Just like friction acts in the opposite direction of motion, drag acts in the opposite direction of motion as well. Same thing as air resistance, so keep that in mind. And if the object is moving through a fluid, it has to have that drag as well, unless it's an ideal condition, of course. Okay, so those are the contact forces. Then we spend most of our time talking about those plus one of the field forces. So I want you to think about this for a second. It is possible to apply a force without actually touching something, but you have to use one of the fundamental forces of the universe. And the fundamental forces of the universe, really there's only two. There's four total, but there's only two that we can deal with on a large scale. So there's this thing called the strong force and this thing called the weak force, and they both act on subatomic particles or atoms. And so we really are not considering those at all. And so rather we're just going to consider the electromagnetic force or the gravitational force. Those are the other two fundamental forces of the universe. So we're going to split electricity and magnetism because it's easier to talk about them differently, even though they're part of the same fundamental phenomenon of the universe. So real quickly, we'll get the electricity and magnetism out of the way here because we spent most of the time this year talking about gravity. Let's say you have a balloon and you've rubbed that balloon all over your hair, and then you pull the balloon away and your hair tries to reach out for it. So you know that your hair is being pulled in some way by the electric charges on the balloon. So each of these little hairs has a little pull, like so. Even if your hair doesn't touch the balloon, it still has that pull towards it. And so you can have there be a space between the balloon and your hair, and you can still feel that force pulling your hair. So what is the cause of that? Well, it's the electrostatic force. Okay, we'll talk more about that right at the end of the school year. Electrostatic forces. And then everybody probably has played with magnets when they were a little kid. So you've got the north end and the south end of a magnet. That's the North Pole and South Pole of a magnet. And if you try to push the north poles together of two different magnets, you'll see that they feel pushes away from each other. So that would be a magnetic repulsion. So we've got magnetic and we've got electrostatic. And interestingly, this can be both attractive and repulsive. Both of those can be attractive and repulsive. So if we wanted to, we could talk about how electrostatic forces can pull things together or push things apart. Or magnetic forces can pull things together or push things apart. That's not the same can't be said for the last of our field forces and the one that we're going to spend the most time on, and that's gravity. Gravity is the big one for us. This course is a lot about gravity. In fact, Newton came up with his laws of motion, particularly to help to describe about gravity. Let's imagine the situation here. You throw a ball into the air. The ball has that parabolic trajectory and then falls back down to the earth. Did the earth touch it the whole time it was in the air? No, it did not. And so what we see is that the earth must have been applying a force to the ball, but through a field, not through contact. And so if you wanted to envision that field, it would look like this. So here's the Earth at the center, and then it has these strong forces coming in towards it that if you're close to the surface of the Earth, and then as you get farther away, you can see the forces get smaller and smaller until finally they get almost zero, but never quite zero. So you always feel that pull towards the Earth or towards any object, but again, it gets smaller and smaller as you get farther away. One last thing real quick. Is it just planets and stars and moons that have this gravitational field? No, everything does. And so check this out here real quick. I'm going to draw it right here. If you, right, and your friend say, hey bro, what's up? Okay, are standing next to each other like that on the surface of the Earth. Do you have gravitational fields that interact together? Yeah, you do. You have a tiny little force that pulls you two together. However, on the surface of the Earth, the gravitational force of the Earth dominates everything, and so you will never, it's very difficult to measure that. However, if I took you and your friend out into space, so put you in a big box out in space, far away from the Earth, and I waited for about 1,000,000 years, that tiny little gravitational attraction between you two would get you closer and closer and closer until finally you touched in the center of the box. Again, it probably would take a long time for that to happen because it's a very, very, very small force, because your masses are very small. But you do produce a gravitational field. Anything that has a mass has a gravitational field. It's just they're mostly too small for us to measure. Okay, hopefully that helps. Let me know if you have questions.